Hello, I will explain here the idea of a very simple classification algorithm called the naive Bayes classifier. It's very easy to implement and it's very easy to explain. So if you have seen my previous video, I explained the problem of predicting the label of certain image, and the label would be either face or not face, corresponding to the case where the image contains face or doesn't contain any face, it contains something else. So you have an image 200 by 200, it contains some pixels, and you want to predict if these pixels form together something that looks like a face or not. And we explained the idea of extracting features and weighting them differently and then predicting a score, and if this score is positive, then we say that this image contains face. If it's negative, it doesn't contain face. So let's ask this question, but from different perspective, from probabilistic perspective. So we want to calculate the probability that the label of the image is face, given the image as input, conditioned on the image. If we use Bayes rule, we know that this is the probability of the image given that it is a face, it's labeled as face, times the probability of the label by itself, and this is what we call the prior. This is a prior distribution. This tells you how many of your image, how many images in the world are roughly faces, okay? Regardless of the actual image itself, just how many out of like 100 images, how many of them should be face, how many shouldn't be face. This is the prior distribution. And then there is one term here that we shouldn't care too much about, and it's the probability of the image itself. Okay, so this is Bayes rule, and that term actually we can ignore it because it will not have any effect for about our decision. What we will be doing is compute the probability that y is face using this equation, and then compare it to the probability that y is not face, and then whichever is higher we can pick that one. So let's look into the probability that y is not a face given the same input image. You can see that this first term doesn't change, it remains the same. It's just probability of x, 1 over probability of x. X is the image, and of course y is the label of the image. This gives us probability of x given that the label is not a face times the probability of not face. Right? So since this term is the same for both cases, we don't need to compute it, we just need to compute this term here, the probability of x given that it's labeled as face, times the prior probability that this is face, and this term also for not face. And then if the first term is bigger than the second one, then we predict that this image should be labeled as face, otherwise we predict that it's not face. So we just compute these two terms and we compare them, and then we return our answer based on which one is the maximum. Let's start with the easy terms, and the easy terms are these priors. So the first term, which is the probability that y is face, is you compute it from your training data. You go through all your images, and some of the images are faces and other images are not faces. You compute the percentage of the faces. Let's say you have 100 training images and 70 of them are faces. So the probability that y is face is 70%, is 0.7. And the probability that y is not face is 0.3. So this is just distribution of face versus non-face in the training data. So we can compute this. If you have just two classes, you can just compute these probabilities for two different classes. If you have more than two classes, like in digits, you have 10 classes, you have to compute the probability of 0, probability of 1, which just indicates in all the numbers written in the word, how often does 0 appear, how often does 1 appear, how often does 2 appear, etc. So you get this, you assume that your data is a good representation of the distribution of this class in the word. So let's go into the first term, which is the probability of x equals face. So the key thing is to compute this probability of x the probability of the image given that it is labeled as face. So the idea of naive Bayes is that we can write this as product of the probability of individual features. We can take this image and break it down into a bunch of features, let's say 12 features, and we compute the probability of each one of these features given that it is that the image, assuming that the image is going to be labeled as face, times the probability of the second feature, assuming that the image is a face, times the probability of the third feature, the feature of the image X, assuming that the label is going to be a face, etc., until we get to the last feature. And in our case, let's say we have 12 features. This is just for sake of example. So I will explain here just how to compute the probability of each one of these features for a specific label, which is face. And then you can do the same thing for if you have for all other labels that you may have. In this case, you have only another label which is not face. So what is this exactly? This means that given this image X, if I want to look into the first feature phi1, I find that this feature takes value 0. There is 0 pixel inside phi1, 0 marked pixel in phi1. So this probability means of all the images in my training data that are labeled as face, how many of them feature 1 takes value 0. And this gives you this probability. Okay, I'll explain it again. So probability of phi1 of x given y equals face is computed in the following. You take your image and you compute phi1 of x and you see what's its value. Let's say the value is 0. For phi2 you will have different value, you'll have maybe 3. So you see in this specific image which value is phi1 taking, and let's say it's 0. Then you say, if I look into my training data and they focus only on the images that are labeled as face, among all those images that are labeled as face, which percentage of them have feature 1 set to 0? And that's the score that you get here. So the way you get this score then, if you want to have more precise representation for this, more efficient, is you go through all your data and you have to fill 2 tables. Okay, so this is what you learn from your data. You have to fill these 2 tables. One table is for all the images labeled as face, and the other one will be for all the images labeled as not face. Okay, you have these 2 tables. One is just for faces. You can use it for computing the probability of x if y is face, and the other one is for not face, and you will be using it for computing the probability of x if y is not face, for a second this term here. And this table has in the rows of this table are features. So you have feature 1, and then you have feature 2, and then you have feature 3, feature 4, etc. As many features as you want. Now, what we have on the columns are the values that this feature can take. So if your features, for example, are binary, then you have only 2 possible values. This is the range where we count here the number of images where feature 1 is, let's say, 0 and 1. Let's say the features are binary, like if the features correspond to pixels, then they will be either 0 or 1. Depending on the range of your features, you will have different possible values. Well, let's say that our features can take values from 0, 1, 2, 3, 4. So we have 4 possible values for each feature. So I'm going to be counting here the number of images where feature 1 has value 0, and then the number of images where feature 1 has value 1, 2, and 3. Same thing here. So let's say we have 4 possible values for each one of these features. Then what I need to estimate from my data, what I need to compute is for all the images that are labeled as face, if I consider only feature 1 of those images, how many of them have feature 1 equals to 0? How many of them have feature 1 equals to 1? How many have feature 1 equals to 2 and equals to 3? And I need to get the frequency of each one of these possible values. So let's say you have 100 images and 40 of them have feature 1 equals 0. So the probability of this feature being 0 is 0.4. Let's say among these 100 images, I have 12 images that have feature 1 equals to value 1. So this becomes 0.12. So we have 4, 12. Let's say I have 8 images where feature 1 takes value 2. So this is 0.08. And let's say you have another 40 images where feature 1 equals to 3. So this should add to 100%, okay? Because these are all the possible values that feature 1 can take. It's either 0 or 1 or 2 or 3. If I add them together all, I would get 100%, okay? And all this is done just for face, for the image labeled as face. Then you repeat the same thing for all the images that the other half of your image, the other subset of your image that are labeled as not face. And let's say here you can have like 0.37, 0.03, 0.5, and 0.1. You do the same thing for all your features, and these become the probabilities that you will be using in your naive Bayes classifier. You take your, so learning is just by estimating these probabilities. The frequency of each feature, take the frequency of each value of each feature for each kind of image. Okay. Then if you want to compute what, if you are given now a new image, completely new image X, and you want to know the probability that this image will be labeled as face, you again need to compute these two terms, and the biggest part is this term, just what is the probability of the image, assuming that it is face, right? What are the odds that if this is face, it's going to look like this, like what I am seeing here. Naive Bayes says that this can be written as the product of all these terms. Now, what are these terms? Each one of them is, you will compute it by following this step. You take the first feature of phi1 and you look into your image that you are trying to test, phi1, and you find out that it has value 0. Okay, phi1 here is 0. So you look into your table and you see phi1 equals 0 has probability 0.4. So you can use here 0.4. Okay, you look into the second feature, and second feature in your image, you count how many pixels, for example, are there, how many market pixels, and you see that there are 3 or 4. There are 3, for example. Let's say there are 3 pixels. Then you go into feature 2 and you see what is the probability. Let's fill this table just for sake of argument. Let's say it's 0.3, 0.3, 0.1, and 0.3. Okay. Oh, this doesn't add. This adds to that one. So let's say for sake of argument that in your data you estimated that frequency of value 3 for feature 2 in faces is 0.3. So you will be using here 0.3. And then you calculate this for all your features and you multiply them together. Now there is one issue that may happen is, what if you get some feature that takes certain value that has probability 0. Let's say for feature 3, value 2 has probability 0. Let's say this is feature 3. Let's say it's 0.1, 0.1, and 0.8, and 0. That means that when you multiply everything by this probability, everything will be equal to 0. To avoid that, you can, one very simple trick you can do, you can just, instead of using 0, use very small number, let's say 0.01, just to avoid making everything equals to 0. Or one other way to do it is you assume that there is some fake example in your training data, just one example, where actually feature 3 takes, it's actually face, and feature 3 takes value 2. And there is this fictive or imaginary example that has that. And then you compute the probability of feature 2 by just taking 1 over the number of all images that have y is face. Okay, and that's it.